Okay, welcome back to the fourth part of our video series for the lecture material of week one. I hope you're still with me. I hope it's not too tiring to listen to this stuff via video. I know it makes you very tired to listen to this stuff and to simply watch videos. That's the downside. On the upside, you can watch those videos in your favorite sweatpants and from your bed. So things could be worse. In the previous video, we discussed instrumental variables, and those will also play a role in the current video, which is dealing with the generalized method of moments. So we already talked a little bit about it because, like we said, that the IB estimator and also the 2SLS estimator, they can be regarded as special cases of the GMM estimator. And as we will see, they are, however, not always the best option. So GMM can actually improve upon these estimators, at least on the 2SLS estimator. And GMM is something pretty useful. GMM is something very general. GMM is something very elegant. And this is why people decided to give Lars Peter Hansen the Nobel Prize for GMM. Even though the method of moments is not new, so there's already Carl Pearson, one of the greatest statisticians of all time. Um, he already was talking about the method of moments. Then there is like Dennis Sargent, who was Lars Peter Hansen's teacher at the London School of Economics. Um, he also discussed the method of moments, and this is why some people think that Lars Peter Hansen simply published his lecture notes and got the Nobel Prize for that. Of course, this is like a complete rumor and well, probably not true. Anyway, it's the gossip that I promised you. Anyway, so let's go to the lecture material, GMM. So again, before we show that IV and 2SLS are special cases of GMM, we want to show why GMM is so nice. So we focus on a very simple cross-section, and then once we understand the mechanics of GMM, we show how to apply GMM in panel data models. Now, a very nice textbook for GMM is the Hayashi Econometrics book. And unfortunately, as always, like there's issues with notation. So Hayashi's notation is different from Wooldridge notation, and it's very difficult to combine them both. I tried my best in these slides, and please recall that Hayashi uses different symbols for the instruments and different symbols for the included explanatory variables of the models. And this can be very confusing. So keep that in mind that the notation in Hayashi is different. Okay, so this is again our cross-sectional model. So we kind of skip the t dimension here. And we say that Z is a vector of valid instruments so that this vector Z is exogenous or is uncorrelated to U. And we can write this simply like that. Okay. Now, by the way, this vector Z is, of course, it can be, it can, for instance, include all the x's plus some additional variables in case it can be a part of these x's. Z can contain the exogenous part of X and have some additional excluded instruments in there. And so it can actually even be X itself. So we will see what happens with Z. So what we will need is that we need at least, we need to identify beta. Okay, so for that, we will differentiate between three cases. So let's say the dimension of X is K, so X is a K vector and Z is an L vector. And if you read Hayashi, it will be exactly the other way around, unfortunately. Yeah. Now, if the dimension, like if we look at this matrix here, this thing, and this has rank k, and the number of instruments is also k, then we say beta is exactly identified because, well, the dimensions of these two vectors match exactly. Now, if this thing here has rank k, so we say that this has full column rank because like the number of columns is governed by x prime here in this case. But the number of instruments, L, is strictly larger than K, then we say that beta is over-identified. And if L is less than K, so meaning we have less exogenous variables than we have potentially endogenous variables, then beta is not identified or under-identified. Yeah, that's precisely what we have here. So if the number of potentially endogenous variables exceeds the number of instruments, then this matrix here cannot have full column rank. So the rank of this thing will be smaller than K. Okay, another requirement for the full rank condition, so the full column rank condition, is that, of course, the excluded instruments are correlated with the endogenous variables. Yeah? So we cannot simply identify beta by dumping kind of useless variables in there. Yeah? So we need that these excluded instruments are again relevant. Okay, now what do we do with this? Well, we define the so-called moment function, gi of beta. And if you look at this, so this is like our exogenous vector of included and excluded instruments, so all exogenous variables. And this thing is simply ui, right? So ui can be written as yi minus x prime beta. Now, if we want to estimate the expectation of this, right? So this is simply our moment condition. If you look at the expectation of gi, this is simply the expectation of zi times ui. That's our moment condition. And again, by the analogy principle, when we estimate a population mean, a population average, then we do that by replacing the expectation by a sample average. So that's a very clearly natural estimator using the analogy principle. Now, if we kind of want to set this thing to 0, which we should do by the moment condition, then it turns out that it's not that easy as long as beta is over-identified. So if beta is over-identified, then we have a system of L equations for K parameters, and therefore there may not exist such a beta tilde such that this thing can be set to 0 exactly. By the way, this n I will change to a capital N, another typo. So we cannot meet this condition exactly. Okay, that's bad. Now, what is the next best thing? Well, we can try to get this thing as close to 0 as possible. So we find a beta such that this thing is almost satisfied. So what we are doing is that we minimize the distance between our gn of beta and the 0, the vector of zeros. Okay, now in order to do that, we need actually a distance measure, right? So, and the distance measure can be based on, for instance, the Euclidean distance. And what you see here is simply the cross product of a minus b and a minus b, right? And that's the Euclidean distance. And here we include also a weighting matrix. Yeah? And we will see that this weighting matrix can play an important role in GMM. Okay, so the distance between two vectors is defined as this quadratic form. Okay, so now we say that Wn is simply some matrix. It can be a random matrix that converges to some matrix W, which is of course then non-stochastic. And the very big condition here is that it is not allowed to depend on beta. This is very important. Okay, so when we do this, then we can define the GMM estimator like this. Yeah? So beta hat, depending on the weight matrix, is the value of beta that minimizes this expression here on the right-hand side. And you see that this is precisely kind of, this is A, oh, sorry, you don't see that. So this is A, B is 0. Yeah, so in our distance measure here, yeah, A is Gn of beta, B is equal to 0, and W is here Wn. Yeah. There is an additional factor of n, which looks surprising, but this is actually meant to be there, and we see why it's there later on. Yeah, so all this stuff here we define to be J of beta Wn. Okay, now How do we find the value that minimizes this expression? Well, that's business 101. We take the derivative and set it to zero. That's like we solve the first order condition. So we take the derivative, set it to zero, and this is the case. Well, basically, this is just taking the derivative. So, of course, you have to be a little bit careful because everything here, this is a vector, this is a matrix, this is a vector. So when taking the derivative, you get matrix, matrix, vector here. Okay, now we have this general expression, but of course, we also have a model, right? Um, okay, so this should actually be Gn, this should be Gn. I will change that also in the next, before I upload the slides. Um, we actually have these expressions, yeah? So we have the derivative of Gn and we know what Gn looks like. Yeah? So for instance, the derivative of Gn, yeah, let's take a look at it again. Gn is this. And if we take the derivative with respect to beta, we have simply that the zi times xi prime stays. Yeah. Okay, this is the derivative. And therefore, once we plug in these things into the first order condition, we get this condition here that looks rather complicated. Yeah? Okay, now let's look at it step by step. So first of all, we define this matrix D, which is the expectation of xi zi prime. And D is kind of for derivative. And you see that it comes from the upper part here. So this is the derivative of G, and D is simply the same thing on the population level. Okay, now we can then write the GMM estimator in the following short way. So we have here D hat times Wn times D hat prime, of that the inverse. So basically we're solving for beta hat here, right? So you simply take all that stuff here with an inverse to the other side, and this is what you get. Yeah? I hope you can see this. Okay, what's the next step? Well, if we want to show consistency of the GMM estimator, this works exactly the same way as for POLS or for IV or for 2SLS. We simply take the condition of our model. So we plug in the right-hand side for each yi that we see. Yeah? So there's only one yi here. And when we do this, again, we get like an expression that looks pretty much horrible. Yeah? So it doesn't look nice, but if you look at it long enough, then you will see that things simplify quite substantially. So you see that, of course, this inverse cancels with this thing so that we have beta plus this part. And of course, the behavior of this part will largely depend on whether this inverse here exists in the limit and whether this thing converges to zero in the limit. Okay, now each, like for instance, if you look at the matrices separately, like D hat converges in probability to some matrix D, because remember what is the form of D hat? Where did we define it? Here, right, it's simply a sample average. And if we assume that the data is IID, this will simply converge to its expectation. So no big deal here, weak law of large numbers. Moreover, we have assumed that Wn is a stochastic matrix, but this also converges in probability to some positive semi-definite matrix. Yeah, so this is kind of what that means. It means that this is semi-definite. Definite. Okay. Now, if we look at this product here in the limit, so if we want this to be invertible, we need that D has full column rank. And well, if we look at what D actually stands for, so it's this thing. And we have seen this before, namely in our rank conditions here. You see that if this thing is exactly or over-identified, then this has full column rank. Full column rank means that the matrix has rank K. Okay, so This thing here is invertible as long as beta is exactly or over-identified. Very nice. And again, we apply the continuous mapping theorem. Yeah, so the inverse is a continuous map exact at 0, but we have assumed that this is not going to 0. So therefore, by the continuous mapping theorem, this thing here in total will converge to the inverse. And here we have these non-stochastic matrices. Yeah, so this is an expectation. This is something non-stochastic, and this is, well, the same thing as, yeah, it's D. Okay, so we have dealt with all these parts. So this is fine, this is fine, this is fine, and the last thing that is left is the last sum in 18. Well, but that's also easy, right? We have, again, we assume IID data, we have a weak law of large numbers, and therefore, assuming that sufficient moment exists, which is not a strong assumption, this thing will converge in probability to its expectation. And since the z's are exogenous, are valid instruments, this thing is 0. Okay, that looks complicated because the expressions are so massive. However, the math is actually pretty simple. It's pretty much the same idea as in the OLS or the IB case. So what we have shown is that no matter which choice of weight matrix you have, the GMM estimator will be consistent for beta as long as n goes to infinity, and of course as long as all these rank conditions are satisfied, so beta is at least exactly or over-identified, and the z's are really valid instruments, so they are orthogonal to the model error. Okay, now, if this is true for any weight matrix, consistency holds for any weight matrix, you may ask yourself, so what's the point of the weights? Why did we even introduce the weights? And this is what we will see in the next step when we look at the asymptotic distribution of the GMM estimator. Okay, now, if you go back to equation 18, and you take beta to the other side and you multiply this side then by square root n, and you get like 1 over square root n here. This is precisely what you get. Now, we have already seen that this term here is unproblematic. The d hat converges to d, wn will converge to w. So all these parts, they converge in probability to nicely defined limits. And now, considering the last part, we can apply a central limit theorem, and we will see that this will converge to a normal distribution with mean 0, right? Because those instruments are valid instruments, and therefore the expectation of zi times ui is 0. And it will have this asymptotic variance. So simply the expectation of zi ui times zi ui in brackets transpose. This gives you this thing here. Okay, because ui is actually assumed to be a scalar. In our case, ui prime is the same thing as ui. So we can simplify this matrix here. We call it V and write it like this. This is, of course, because we look at a simple cross-section here. When we go back to panel data, we have a stacked data, so ui will be a t vector again. Yeah? So keep that in mind. Okay, so pretty much everything, we know the limits of the different terms individually. So now the only thing that is left is that we have to combine everything. So, and when we combine different convergence types, we use the Slutsky theorem. And what does Slutsky say? Well, remember, if one thing converges in probability to some constant and some other random variable converges in distribution to some other converges in distribution to some distribution, then the whole thing converges in distribution. Okay, so the weaker form of convergence is the one that survives. And well, simply applying the Slutsky theorem, so we get the normal distribution. You see here's the V matrix, And now this, of course, makes it look complicated. Yeah? So I agree that GMM is not pretty at first. Huh? So we have here normal distribution with mean 0 and variance v, and we multiply all that kind of stuff to it. Yeah? So when we do that, we get a variance, this whole bunch of matrices times V times this transpose. Yeah? And this is why it looks so ugly. It looks really ugly, and you have to look at this stuff for a while to see how this can be simplified. Yeah. Um, so this is of course a question that I would normally ask in class, and normally people would sit there, stare at the wall, stare at the board, and nobody sees it. But if you actually choose W to be the inverse of V, then the whole thing, the whole bunch here, simplifies to DVD. D V inverse D prime inverse. And this is again something that we've seen many times before. We have a sandwich form variance. And this sandwich form here on the right-hand side of 20 is a really nice, it's a fantastically tasty sandwich. So because it is the smallest sandwich, let's say it has the least calories of them all, it's the smallest sandwich with respect to the Löwner ordering. Now, what is the Löwner ordering? If you have two matrices A and B, then A being bigger in terms of the Löwner ordering than B means that if you take A minus B, the resultant matrix will be positive semi-definite. Okay, so what we see, because this is really the best matrix, the best variance matrix that you can find, we call a GMM estimator that uses the optimal weight matrix simply optimal or efficient. Okay. Now, of course, the question is, how do we construct an estimator of V, let's call it V hat, such that, yeah, well, we get a consistent estimator. Okay, let's try the following. V hat is, well, simply V, just that, okay, let's take a look at what was V again. So this is what V looks like. And we replace the expectation, there's a population mean, by a sample mean. And wherever something is not observed, recall that this is the model error that we can actually not see in the data, we put a head in it. Yeah? So we estimate it. So these U heads here are simply estimated as residuals. Yeah, so U hat is business as usual, yi minus beta hat prime xi. Okay, now if you look at our way of estimating V hat, so it looks a bit circular, right? So kind of in order to find the best GMM estimator, we actually need an estimator. So it looks like the cat is biting its tail, but however, recall that the optimal weight matrix is relevant for asymptotic normality, whereas a beta that is consistent, we don't need the optimal weight matrix. We can use any matrix. Yeah? So beta hat Wn is consistent for any choice of weight matrix. So naturally, this suggests a two-step procedure. In the first step, we choose any weight matrix such that, this should also be a capital N, I should change that, such that, well, the limiting Wn is some matrix W, which is positive semi-definite. For instance, an easy choice is that you simply use the identity matrix. Easy. Huh? Now, using this initial weight matrix, you compute the GMM estimator. And with this GMM estimator, you compute the residuals. And with the residuals, you compute the estimator for the optimal weight matrix V hat. And well, yeah, once you have the optimal weight matrix V hat, you simply compute the GMM estimator using the estimate of the optimal weight matrix. Yeah? So if we quickly go back, what would you compute in the second step? Well, where are we? Sorry. Ah, yeah, here we are. You would simply replace this Wn by V hat inverse. which is the optimal weight matrix, and recompute the whole minimization problem. And this would give you the two-step optimal GMM estimator. Okay, wonderful. Now, of course, whatever you choose in the first step is in principle fine in theory, right? So because this thing does not influence consistency, and consistency is all that we need in order to get a two-step optimal GMM procedure. Of course, in small samples in application, the choice of WN in the first step can make a difference. Yeah, so some people use the two-stage least squares estimator in the first stage in order to get like a consistent estimator. Other people use simply the identity matrix. Another remark is that GMM is so nice and so general because it also works when GI is a nonlinear function of the data. Yeah? So um, the problem with the nonlinearity is not really a theoretical problem. The only problem is that if you look at the first order condition and all these, again, this should be a GN, this should also be a GN. I will change that. Um, these things will be nonlinear and therefore there will be not, you will not find a closed form solution for your beta hat. Yeah? So that's the issue, and you have to rely on numerical methods to find the GMM estimator. Okay. Another thing that you should see is that when you have beta exactly identified, then we have the same number of equations as we have parameters, and therefore we can always find some beta tilde such that the distance between gn of beta tilde and 0 is exactly 0. And in that case, the GMM estimator simplifies, well, um, so this beta can then be shown to be this. You can check this, that's very easy actually. And this is also familiar to us. This is the classic IV estimator. Yeah, so therefore the IV estimator is a special case of GMM. And moreover, you can also get the two-stage least square estimator by using a particular weight matrix. Yeah? So if you use this weight matrix, then GMM will be simply the two-stage least squares estimator. Um, Another remark is that, at least that is part of the exercise, not for this week, but probably for the week after, is that GMM is optimal, yeah, and because 2SLS is a special case of GMM, that means that there's likely situations in which GMM is better than 2SLS. However, if your error terms are homoscedastic, meaning that the variance of the U does not depend on the level of X, then it turns out that there is no advantage of GMM over 2SLS. Okay. Yeah, so now this is something pretty cool. It's called the J test. So this is going back to why we actually put this factor n in our minimization problem when we defined the GMM estimator. Maybe I can quickly go back to 16. Yeah, so you look in 16, we have this additional factor n when we define j. However, in the computation of the GMM estimator, this doesn't make any difference, right? So if you kind of find the argument of this, the whole thing, it's the same as this, because this is simply a constant, right? So this 2 times n here drops out of the first order condition. So it's completely irrelevant. So the question is, why did we actually put this n there? Well, and this is what we will see now at the j-test. Whenever we have beta over-identified, meaning we have more instruments than we have we can use the j-test for, well, basically testing the model. Recall that if beta is the true value, then square root n times gn, again, this should be a capital N, converges to a normal distribution with a variance matrix V. And therefore, if you plug in if you put v hat inverse into the j statistic, into the definition, that's what I write here on the right hand side, then you take this n, you put square root of n in front of this, you put square root of n in front of this. This thing here converges to a normal distribution with mean 0 and variance v. The same thing for this thing here. And therefore, if you take the inverse, this will cancel out the v in this part and in this part. And therefore, the whole thing converges to a chi-square distribution with L degrees of freedom. Yeah. Okay, well, L, remember that, is the dimension of the instruments. Okay, that's pretty cool, right? So we have now like basically the test idea is the following. So if the model is really, so if all the assumptions for GMM are true, then we know that the J statistic will converge to a chi-square distribution with L degrees of freedom. So we can actually test the model now, right? So if we observe that the J statistic is very large, and it's actually larger than, for instance, the 95% quantile, uh, percentile of the chi-square distribution with L degrees of freedom, then we can reject the null hypothesis that all the model conditions are met. Okay, now there's only one problem. We do not have the true beta. We don't know this thing. So we have to estimate that first. And it turns out that, as usual, when we estimate stuff, we can only do that at a loss. And the loss here is that we lose some of the degrees of freedom. Yeah, so we lose from L, we go to L minus K, which is exactly the number of valid excluded instruments. This is why we need over-identification in order to apply the J test. Okay, so here's again the idea of the J-test. This is our null hypothesis. The model is correctly specified. And if you find that your J hat is too large relative to the 1 minus alpha quantile of this distribution here, then you will reject the null hypothesis and you know, well, your GMM estimator is probably inconsistent. Now, this sounds very good. We can somehow test, like this is the interpretation that people normally have, right? So this J test is normally interpreted as a test of the instruments. People think that the J test tests whether all the Z's are uncorrelated with the model error. Now, this is of course was partially true, right? So if this condition is not true, then the J test is likely to reject, because like this is of course part of our correct model specification. And therefore, if this is violated, the model is incorrectly specified and we should reject. Now, one thing to notice is that the J-test only works when we can find a consistent estimator in the first stage. In the first, I mean, we need to do a two-step optimal GMM, and we need first an initial estimator that is consistent. And in order to find a consistent estimator, we actually need at least one instrument that is actually exogenous, right? So once we have one instrument of which we know for sure that it is exogenous, we can test the exogeneity of the remaining instruments. Okay, now one problem that you can see in applications is that even if all the instruments are actually valid, so this condition is met for all the instruments, however, your model is actually not a linear model, but it has some nonlinearities that you did not account for, then also the J-test is likely to reject, because again, your model is in total not correctly specified. And one other big problem is that people did simulation studies and they saw that, well, if you are in a small sample, then the J-test is kind of too pessimistic. So this is one of the reasons why people don't like the J-test so much anymore nowadays. So whenever you do some applied work, I think it's a good idea to simply look at the J-test, but you don't see it that often anymore in academic papers. Okay, so wow, um, that was quite a bit already. So, but however, GMM continues a little bit. Um, GMM is super flexible, so it's generalized for a reason. For instance, we can look at the system of equations again, where we observe the same individuals in two different equations. So these are variables, two response variables, and the individual is the same. So this is why we drop here the I index. And now you have some sort of theory that suggests that the effect of x12 on y1 is the same as the effect of x21 on y2. Yeah? So this is like what you mean with this condition here. Now we also assume that all the x's here are uncorrelated with the model errors. Now, how can we frame that in GMM? Well, first of all, we take all the remaining parameters. Yeah, so notice that there is no beta 1 here because beta 1 is already captured with alpha 2. Yeah, so we now have 5 parameters. We also stack the y's, we stack the u's, and we define x1 tilde, which contains all the variables for the first equation. And we do the same thing for x2. But notice, of course, that yeah, the way especially x2 is written. Yeah? So those are written in such a way that if we take x1 prime gamma, we get the first equation, and x2 prime gamma should give us the second equation. Okay, now we have to continue with our definitions. So we have this big matrix XD. And now the important thing here is that this is actually a 6 times 2 matrix. Yeah, so the dimension here, it has 6 rows. And XM is simply the stacked version of our X tildes. And with these definitions, we can define the expected moment function. So GI is this thing here in the middle. Yeah, so this is this system of equation written in matrix and vector notation. And what we see is that the dimension of this thing, the dimension of GI will be 6, right? So this is 6 times 2, this is 2 times 1, this is 2 times 5, this is 5 times 1. So this thing here is 2 times 1, this is again 6 times 2, so the whole thing will be 6 times 1. Yeah? So this is a vector, a 6-dimensional vector of zeros. Therefore, we get 6 moment conditions for only 5 parameters to estimate, and therefore gamma is over-identified, and we can use two-step optimal GMM. Now, oh yeah, well, I hope it's clear how to do this, right? In the first step, you choose any weight matrix, for instance, the identity. You compute the GMM estimator. With that, you compute an estimate of the optimal weight matrix, V hat inverse. And with that, you recompute the GMM estimator and you get the two-step optimal estimator. Okay. Now, finally, back to panel data. We again have a model. That model we have seen many times before. Let's say all the x's are nice. So if we stack them together in the usual way, then we have this condition. So they are all uncorrelated with the model error. And yes, now there's actually a couple of ways of using GMM here. Yeah, so this is contemporaneous uncorrelatedness. And of course, an implication of this assumption is that we have pooled contemporaneous uncorrelatedness. Yeah, so when we pool them together, these moment conditions, meaning we take the sum over t, then it turns out that we have exactly k moment conditions for k parameters to estimate, and therefore beta is exactly identified. Yeah, so if beta is exactly identified, then GMM is very simple because we can make the distance between the moment function and zero equal to zero exactly. Yeah? So we don't have to do all this minimization business. And we can show that the GMM estimator would be beta hat. And this thing here is familiar. Yeah, so this will coincide with the pooled OLS estimator. And by the way, here there is a sum missing. So here should be a sum over I, and here's a sum over I. I will fix that in the slides. Okay, now we can also do GMM in a different way because our assumption, contemporaneous uncorrelatedness, is actually stronger than the pooled version that we just used. So we can actually also over-identify the beta, right? So we call that each of those x's is uncorrelated with the UIT in the particular period. So this is uncorrelated with UI2, this is uncorrelated with UI1, this is uncorrelated with UI capital T. Yeah, so let's define this thing. And yeah, so we can write contemporaneous uncorrelatedness in this matrix form. And if you look at this, we have now t times k moment conditions for only k parameters to estimate. So if we have an actual panel data set, meaning that t is at least 2, then beta is now over-identified and we can do two-step optimal GMM. So in order to do that, we define the moment function, which we see here, and then, well, business as usual, right? In the first step, we choose an initial weight matrix, for instance, simply the identity matrix. And well, we do an initial minimization to get like an initial estimator beta tilde. With that, we compute an estimator of the optimal weight matrix, V hat inverse. And with that, we repeat the minimization procedure and get the two-step optimal GMM estimator. Okay, yeah, that was quite a bit about GMM. So I hope you found GMM as elegant as, well, the rest of the world does in the econometrics community. I hope it was more or less clear. And well, that's it for this video. See you in the next one where we finally start exploiting the true power of panel data models. Bye bye.